This video is on section 10.6, plane curves and parametric equations. Here are the objectives for this section, and basically what we're going to be doing is talking about different parametric equations. And what's nice about parametric equations is that these equations help us identify the time, which is the parameter, at which an object is at a specific point. And that's what we're going to work towards. So here are a few definitions. The plane curve is going to be defined by the points. The ordered pairs now become this. So x at a value of t and y at a value of t. And again, t is called the parameter. And parametric equations basically are two equations, but together they create a graph of a line or something of the sort. So when we graph the plane curve, basically what we're going to do is we're going to just plot ordered pairs, but they're going to be plotted in order of an increasing value of t. And then we're going to sketch in some arrows that indicate the orientation or the direction in which this graph takes. So really, it sounds a little difficult, but all we're going to do is we're going to pick increasing values of t, which represent time, and then find the corresponding x and y for that, which will create the ordered pairs, which we will plot. So let's take a look. Here is our first example, and our parametric equation is this. So notice we have one equation for x, one equation for y, and we are interested in values of t from -3 to 9, where -3 is not included, but 9 is. So what we're going to do is we're just going to make a table, and we're going to plug in increasing values of t. Now, I only want to use values of t between -3 and 9, and we're going to be plugging these values of t into this equation and here. So since I'm dealing with a fraction with a denominator of 3, it might be wise to choose multiples of 3 within this interval. So -3, 0, 3, 6, and 9 would maybe be wise choices. And then we're just going to plug it into the equation. So when I plug t in here, -3 divided by 3 is -1, 0 divided by 3 is 0, 3 divided by 3 is 1, 6 divided by 3 is 2, 9 divided by 3 is 3. I'm going to do the same thing here. So -3 minus -3 - 4 gives me a -7. 0 minus 4 is -4. 3 minus 4 is -1. 6 minus 4 is 2. And 9 minus 4 is 5. So I've just created each of these ordered pairs, and I'm going to plot those. Now, one thing to be cautious of when we're plotting these, since -3 is not included here, this is going to be an open circle, and then everything else is included in our interval, so they'll be closed circles. So first I have -1, -7 open, 0, -4, 1, -1, 2, 2, and 3, 5. Since I'm only interested in this interval, my graph will look like this. Now, I also want to place the arrows indicating increasing values of t. Well, I started down here and then the values increased. And there you have it. Let's try this one. We're going to do the exact same thing as before. We have two equations, this one, and this is our interval. Okay, so notice that -4 is not included, but 4 is. I have a denominator of 2, so it might be wise to choose values of t that are multiples of 2, just so you're not dealing with fractions. So I'm going to choose -4, -2, 0, 2, and 4. And again, it's your choice what you choose, but you want to choose enough values that it will help you identify what the graph looks like. So now I'm going to plug these values of t in here. And when I do, I get 2, 0, -2, 0, and 2. And when I plug them in to the equation for t in this equation, I get -2, -1, 0, 1, and 2. Like the previous problem, this will be an open circle and the rest will be closed circles. So when I sketch this, I will have an open circle at the ordered pair 2, -2, closed circle at 0, -1, -2, 0, 0, 1, and 2, 2. So when I sketch this in, it takes this shape, so the arrows, the points went in this direction, so that's the way the arrows should go. Now, sometimes it is helpful to eliminate the parameter. And the reason we would want to eliminate the parameter, which again is often t or time, is so that we can convert these parametric equations to an equation with rectangular coordinates, or x and y only, so that it's something more familiar. And these steps will tell us how to eliminate the parameter. Basically, it becomes a system of equations. So you'll solve one system for t and solve by substitution. Now, the thing that you'll want to remember to do is to identify any domain restrictions. So, you know, if you started off with something involving a radical, make sure that you take those that domain into account. And I'll address that as we move forward. So here is some type of example that you will see. The first thing it will say is eliminate the parameter. Then it will want you to sketch the curve and of course indicate the orientation. And again, when it says indicate the orientation, that just means draw in the arrows. So looking at this, what I want to do in order to eliminate the parameter is I need to get rid of t. And the way I'm going to do that is by simple substitution. Now, in this particular case, this example is a little bit different than some because I have an exponent of t. So what I can do is I can divide both sides by 4 here. So you just pick an equation and modify it. And this leaves me with e to the t is equal to x divided by 4. Well, in this particular problem, there's no need to solve for just t because I have an e to the power of t here. So I can go ahead and take this and substitute it in for e of t. So y becomes -3 times, instead of e to the power of t, I have x divided by 4, and then this plus 4. I can go ahead and rewrite this as y equals negative 3/4 times x plus 4. I have eliminated the parameter t because this equation no longer has any t's in it, and it is something that we are more familiar with. In fact, this is an equation of a line in slope-intercept form, where negative 3/4 is the slope and the y-intercept is 4. Now we do want to address the domain. Now up here, if I have an equation of e to the power of t, e to the power of t looks something like this, which means no matter what, we are always going to have positive values for y. Oh, I apologize. I'm looking at this equation here. So these represent values of x. So our domain then has to involve all values greater than 0 due to that implied restriction. So what I'm going to do now is just graph this equation of the line. So the y-intercept is 4. This should be an open circle because of this implied restriction. So then we'll go down 3 to the right 4, down 3 to the right 4, and our graph will end up looking like this with these arrows to indicate the orientation. Let's try another one here. Now in this case, when we eliminate the parameter, what I'm going to do is I'm going to choose this equation and solve it for t. To do that, I'll divide both sides by 8. So t is equal to x divided by 8. Once I have one equation solved for t, I'm going to take it and plug it into the other equation. So this becomes y equals negative 6 times x divided by 8 plus 4. Remember, you can put the negative 6 over 1, multiply across the top, across the bottom, and simplify. So we have y equals negative 3/4 x plus 4. And it is just a fluke that this ended up being the same thing as the previous example. Now here's one difference. There are no restrictions on either of these original equations. They're both equations of lines. Nothing crazy is happening. So in this case, for our domain, there are no restrictions on x. So this line will extend forever to the left and forever to the right. So everything will be closed circles. From the y-intercept, we go down 3 to the right 4, down 3 to the right 4. Oops, sorry, that's not very straight. And the same orientation. This example will give us something other than a line, but it's the same rules. So looking at this, what I want to do first is kind of identify what the domain should be. So I'm going to look at this and this. Now I know that if I have this interval, it's one revolution of the unit circle. So I'm going to start at 0 and end at 2 pi. Well, if I plug values in for t between 0 and 2 pi, I know that everything is going to be sandwiched between 3 and negative 3. In fact, if I graph this cosine equation, I know that the amplitude is 3. So the maximum value and the minimum value will be 3 and negative 3. And these are values for x because this equation said equal to x. Similarly, over here, everything for y will be sandwiched in between negative 4 and 4. So this will be my domain. because they're the values for x. Okay, now solving for t in one of these equations gets a little tricky because I would have to apply an inverse trig function. So what we're going to do is we're going to take a different approach, and chances are this is not something that you would have thought of on your own, and that's perfectly fine. But this is an approach that you'll want to take moving forward. So what I'm going to do is I'm going to get cosine of t by itself and sine of t by itself. So I'm going to divide by 3 to get cosine of t, and I'm going to divide by 4 to get sine of t. Then I'm going to dig deep in my memory and recall that there is a Pythagorean identity which states cosine of t plus cosine squared of t plus sine squared of t is equal to 1. Well, in this particular case, I know cosine of t and I know sine of t, so I'm just going to substitute those in. So x divided by 3 squared plus y divided by 4 squared is equal to 1. I'm going to square everything, and I find that I have x squared divided by 9 plus y squared divided by 16 is equal to 1. I have eliminated the parameter because I do not have multiple equations with t involved. So this is my equation. Hopefully you recognize that this is an equation of an ellipse with a vertical major axis. So the center is 0, 0. I'll go up 4 and down 4, right 3 and left 3, and I have this ellipse. Now, sometimes identifying the orientation is a little tricky. So remember, in order to find the orientation, you can always make this t-chart, plug in increasing values of t, so try 0 and pi over 2, and then find the corresponding x and y values. So this would be 3, 0, so here. And then this would be 0, 4, which would be here. So you can tell that the orientation is going to be in this direction. Another type of equation or type of example you will see is writing parametric equations. Now, the thing about parametric equations is that there could be multiple parametric representations for one rectangular equation. So what we've done here is I have given you this, and what I'll want you to do is plug this here in to the equation for y in order to find your set of parametric equations. So remember, when you have parametric equations, you're going to have x equals something, which is given to you, and then you'll have y equals something, which you'll find by plugging this in. So when I plug that in, I have y equals 5 times 2/5 t minus 2. When I solve that, these 5's cancel out, and I'm left with y equals 2t minus 2. So my parametric equations would be x equals 2/5 t, which was given, and y equals 2t minus 2. So this whole thing would be my answer. Okay, so for part B, this is part of my answer, but to find the other part, I'm going to take this and plug this in for x, because x represents 2t plus 5. So y equals 5 times x, but instead of x, I'm using 2t plus 5. Don't forget the minus 2 at the end. So this becomes 10t plus 25 minus 2. So this becomes 10t, so y equals 10t plus 23. So my parametric equations are x equals 2t plus 5, which is given, and y equals 10t plus 23. Okay, so here we want to write parametric equations for t to define this given graph. So looking at this, we know we have a graph of a line. And I want to remind you that there are going to be many possible answers for this. Okay, so given this line, I can tell that my y-intercept is 4, and I also know my slope is 1. So this equation in rectangular form is y equals x plus 4. Y equals mx plus b. Okay, so this is the rectangular form. Well, what I need to do is I need to think of some value for x involving a t, and that will be my first part. So you can let x be anything you want as long as there is a t involved. It can be anything. In fact, it can be something as simple as x equals t. If x is equal to t, then plug this in here to find y. So y is equal to t plus 4. And that is really all there is to it, because now you have your parametric equations. X equals t and y equals t plus 4. Maybe you wanted to get a little fancier, and so this is one possibility. Another possibility would be let x be t plus 1. Okay, well, if x is t plus 1, you're going to plug all of that in there. So y equals t plus 1 plus 4, or y equals t plus 5. So this would be another representation. Go ahead and try this on your own, but the values for x are given to you. Okay, so in part A, x is equal to t, so I'm going to plug this in here. So that means y is equal to 2t minus 3. Done. But as soon as we have something a little more exciting than just t, more simplifying is involved. So here, if x equals negative 4t, when I plug that in, I get 2 times negative 4t minus 3. Simplifying that, I get y equals negative 8t minus 3. So this and this are my parametric equations. Okay, in part C, x equals t divided by 5. So when I plug that in, I get 2 times t divided by 5 minus 3. This becomes y equals 2/5 t minus 3. So this and this are my parametric equations. Now, all of this leads to applications. And they're really, again, I mentioned this at the beginning of the video, but these parametric equations are useful in describing objects in motion. And there are really two common applications: linear motion and then projectile motion. So uniform linear motion would be something like moving on a straight path, like a bike being ridden down the street or something. So these two equations would represent our parametric equations. and the initial position is represented by this ordered pair at a time of 0. So our goal would be to find values for A and B. Okay, so this is the linear motion. Then projectile motion is like a ball being kicked up into the air. Okay, so what goes up must come down. So it's going to take on a parabolic shape, and that's why we have something squared. So in this case here, we have a lot more going on. Theta represents the angle of the launch. V naught represents the initial speed or the initial velocity. Then when we get to this equation here, G represents the acceleration due to gravity. And depending on if we're given information in meters or feet, we'll use a different number. Okay, so we're going to take these two different models and do a couple examples, one of each. So here is our first example. Go ahead and pause the video and read through this so you understand what's going on. But what I want to do is I want to represent write some parametric equations that represent this motion for some object going from point A, so this is the initial, to point B, and that takes place over 3 seconds. So if this is my initial point, then I know that x naught is 3 and y naught is 8. Oops. I know t is 3. And as indicated previously, we want to find A and B. And I'll just remind you that from the previous slide or an earlier slide, x equals x sub 0 plus a t, y is equal to this. Okay, so we know these two values. We know the time, and we're also given another ordered pair, so we know x and y also. So x is 6, y is 10. So from this, I have everything I need in order to find A and B. So I'm just going to solve for A here. When I solve this for A, I have x minus x sub 0 divided by t is equal to A. And I'm going to plug in all of this given information here. So x, again, is 6, right here. The initial value for x is 3 divided by time. This is equal to 1. So we have just found A to be 1. I'm going to do the same thing with B. When I solve for B, I have y minus y sub 0 divided by t. Plugging in the given information, I know y is 10. The initial value for y is 8 divided by 3. This simplifies to 2/3, so B is 2/3. Now I have everything I need in order to represent or to write my parametric equations to represent this linear motion. So x is equal to 3 plus 1 times t, or t, and y is equal to 8. Oops, this should be a plus. I apologize. 8 plus 2/3 times t. And there you have it. This last example is an example involving projectile motion. So you can go ahead and pause this, and I'll remind you that we have these two equations. and y equals -1/2 g. And in our case, we're dealing with feet, so we're going to plug in 80 for g times t squared plus the initial velocity times sine of theta times t plus the initial height. Okay, so let's read through this equation and try to identify each piece. So we know the initial height is 5 feet, so this is y sub 0. This is the initial height. The initial speed is 80, so this is the initial velocity. The angle is theta, and we want to first write parametric equations to describe this path, and then once we've done that, then we are going to determine when the ball hits the ground. The ball is going to hit the ground when the height is 0. Remember, y represents the height, so we want to find when y equals 0. So essentially what's happening is this ball is being thrown at, it's starting at 5 feet, it's going up and coming down, and we want to find when it hits the ground. Okay, so the initial time is 0 when the height is 5, theta is 60, and the initial velocity is 80. So this is what we need to plug in to our base equations, so I'm going to do that now. So x equals, the initial velocity is 80 times cosine of 60 degrees times t plus 0. If I simplify this and find cosine of 60 degrees, I end up getting x equals 40t. This is the first part of my set of parametric equations. I'm going to do the same thing to find y, just plug in everything I know. So I have -1/2. I already said that we're going to use 32 for g, and that's because we are dealing with feet. So if you look at the previous slide, if we're dealing with feet, then we're going to plug in 32. This is multiplied by t squared plus 80 times sine of 60 degrees times t plus an initial height of 5. Okay, now I'm going to simplify this, and I get y equals -16t squared plus 40 times the square root of 3 times t plus 5. So this and this together give us our parametric equations. So we have just solved part 1. On the next slide, I'm going to solve part 2, which is determine when the ball hits the ground. So we want to find out when this ball hits the ground, and that will happen when y is equal to 0. Well, I don't have anything involving y here, but I do here. So I'm going to plug 0 in for y and find t. When I find t, t represents a time, so that will tell me when the ball hits the ground. Now, one thing I want to mention is that if I extend this, I'm going to end up going back in time, which is not what we want to do. Notice that there are 2 values in which the height is 0. We will not want this one because it will be negative, so we will only want this answer. So just know that as we move forward. Okay, so setting this up, we will have 0 equals -16t squared plus 40 times the square root of 3 times t plus 5. Now looking at this, you could try to factor it, but it's not going to be easy. So I would just jump straight to the quadratic formula. And when you do that, remember you have t, since that's our variable now, is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Now I'm going to let you go ahead and plug this into your calculator because I do believe you're capable. And you will find that t is approximately two different values, negative 0.07 and 4.40 seconds. It was already discussed that we will not use the negative value. So this is our answer. So you could say something like, it will take approximately 4.4 seconds for this ball to hit the ground. And that concludes section 10.6 and also chapter 10.